In this section, we'll review some properties of power series. A power series centered at the point x naught is an expression of the form sum from n equals 0 to infinity of a sub n times x minus x naught to the power n, which we can write out as follows: a naught times 1 plus a1 times x minus x naught to the power 1 plus a2 x minus x naught to the power 2 plus etc. And so each of these terms here corresponds with one value of n. This is the case n equals 0. This is the case n equals 1. This is the case n equals 2. Here, x is the variable and a sub n's are constants. We say that the power series converges at the point x equals c if the infinite series of real numbers sum n equals 0 to infinity of a sub n times c minus x naught to the power n converges. That is the limit of partial sums given by limit as capital N goes to infinity of the sum from n equals 0 to capital N of a sub n times c minus x naught to the power n exists. So let's write this out. Let's write out a few terms of this partial sum. So this is the limit as capital N goes to infinity of, and then the first term is a naught. Second term is a1 times c minus x naught to the power 1 plus a2 times c minus x naught to the power 2 plus all the way up to a sub capital N times c minus x naught to the power capital N. And so we plug in c for x in each of these terms. So you would try to figure out what this partial sum is for capital N and then take the limit as n goes to infinity. If this limit does not exist, the power series is set to diverge at x equals c. Now observe that a power series is always convergent at its center x naught, because if we plug in x naught for x, we get the following power series: sum n equals 0 to infinity of a sub n times x naught minus x naught to the power n. So what you get here is a naught is your first term, and then plus a1 times x naught minus x naught, which is 0, plus a2 times x naught minus x naught squared, plus etc. And each of these terms, except for the first one, is 0. So when you add this all up, you get a sum that is equal to a naught. And so that's independent of what your value of capital N is. You'll always converge. So what can we say about convergence for other values of x? And here's a main theorem from power series about the radius of convergence. For each power series of the form that we can see over here, the sum from n equals 0 to infinity of a sub n times x minus x naught to the power n, there is a number rho, where rho is between 0 and infinity, 0 and infinity included, called the radius of convergence of the power series, such that the series converges absolutely for when the absolute value of x minus x naught is less than rho, and diverges for values x minus x naught in absolute value greater than rho. If the series converges for all values of x, then we say that rho is infinity. And when the series converges only at x naught, then rho equals 0. So we have a interval of convergence that goes from x naught minus rho, the radius of convergence, to x naught plus rho. Outside that interval, the power series diverges. Now, at the edges of the interval, we would need to check convergence separately. So at x minus rho and at x plus rho, we need to check convergence separately. And we could have that the series, the power series, converges in both endpoints. It could diverge in both endpoints, or it could be a combination. It could converge in the left endpoint and diverge at the right endpoint, or vice versa. So that convergence needs to be checked separately. Now, the most common way for testing the radius of convergence is by looking at the limit of consecutive coefficients in the power series. So if for n large, the coefficients a sub n are non-zero and satisfy that the limit as n goes to infinity of the absolute value of a sub n over a sub n plus 1 equals L, where L is a value between 0 and infinity, then the radius of convergence of the power series sum from n equals 0 to infinity of a sub n times x minus x naught to the power n is rho, and rho equals L in this case. So we'll see some examples of that in the next video.